In this video, we're going to be discussing the basics of SPI, so Serial Peripheral Interface, as it applies to hardware and PCB design. The two PCBs you're seeing here, for example, on the left-hand side, we have this micro quadcopter control PCB that I designed, which features various sensors, peripherals, motor drivers, and so forth. But for example, also this STM32U5 microcontroller in the center, which interfaces, for example, to the bottom left, to this inertial measurement unit via Serial Peripheral Interface, or SPI for short, transferring data to and from the sensor. Similarly, also the barometer, which transfers pressure data and pressure measurements back to the host controller via SPI, and for example, this CC2500 RF transceiver, which I can use to communicate, for example, with a base station. The interface between the controller, this STM32U5, and the peripheral is via SPI. So SPI can be used to transfer data between a controller and peripheral, or one controller and various peripherals, and it's a very, very common interface used today, and sort of a medium bandwidth interface. Similarly, on the right-hand side, we have similar scenarios where we have one controller, for example, this AMD Xilinx Spartan 7 FPGA, which interfaces via I2S as well as SPI to the Cirrus Logic CS4270 codec. So this contains ADCs and DACs in one single IC. The SPI connection in this case is there to set up the registers internally to the CS4270, for example, to set up sampling rates, bit depths, protocols, and so forth. So SPI can be used for data transfer from, for example, sensors. It can be used for inter-processor communication, as a control interface, and more. And it's a very, very common interface, so I thought it'd be good to make a video detailing the essentials, what you need to know to incorporate SPI into your own hardware and PCB designs, for example, looking at pull-ups, termination, the signaling itself, and more. I did make a very similar video very recently on my channel, and that's to do with I2C, and that goes over the hardware and PCB design basics, and we're doing the same thing today for SPI. The PCBs you saw at the start were both manufactured and assembled by PCBWay in China, and they did an absolutely fantastic job. I oftentimes use their PCB prototype service as well as their advanced PCB service, which I actually use most because this gives me the most amount of flexibility. I can either do through-hole boards or even HDI boards with micro vias, blind and buried vias, a layer count up to 60, and pretty much any customization option you can think of. In addition to that, they also have an assembly service where they can source all parts for you, and they always do a very, very good job. Make sure also to follow PCBWay on Instagram to check out all the new designs they're producing and manufacturing and by their customers. And for example, you might occasionally spot some PCBs of mine there as well. One last message before we start. If you're attending Embedded World 2024, that is the 9th to 11th of April in Nuremberg, make sure to stop by the Federwell booth, which is in Hall 5, booth number 5-316, where Robert Ferenek and I will be there, and we really look forward to seeing you there. If you're attending and you do have a chance to say hi, make sure to grab one of these free Phil's Lab coasters, which I'll be handing out there. During the Embedded World, PCB Arts are also doing one of their tech meetups in the Zollhof on April 10th, and I'll leave links to this in the description box below. But this is where a lot of tech, hardware, and PCB design enthusiasts have a chance to meet up, casually discuss ideas, what they're working on, and anything, of course, they're interested in. I'll be there, and I believe Robert Ferenek will be there as well, so make sure to stop by, and I'll leave links to get your tickets in the description box below. This is a free event. Let's start off by going through the SPI basics. I'll leave some more links in the description box below. In case you're interested in more detail, we'll be glossing over the essentials we need so we can design hardware with this SPI interface. As we said initially, SPI is effectively a medium speed bidirectional interface, even though it can be used unidirectionally, and medium speed is of course up for debate. It's a very common interface, but for example, a controller, this could be, for example, a microcontroller or an FPGA, anything that has the capability to drive the SPI lines, as we'll see later. For example, you'll need a controller that can interface or connect to maybe another controller that acts as a peripheral, or between sensors, ADCs, DACs, and so on, for control, for transferring data, and more. This is a synchronous interface. For example, in comparison to UART, Universal Asynchronous Receive Transmitter, we have a dedicated clock line. Typically, the configuration is that we have a single controller. This is called the master, or typically was called the master. These days it's called the controller, with multiple peripherals. We can see this on the right-hand side where we have one microcontroller, for example, the controller hooked up to various peripherals. These could be sensors, SD cards, and more. SPI is typically, if the controller and the peripherals allow, of course, full duplex capable, meaning we can send and transmit at the same time. In terms of clock speeds, typically you will see sensors capable up to 10 MHz clock speeds and up to about 10 megabits of data rate, but of course that entirely depends on the sensors and peripherals and controllers you choose. You might have to go far lower than that, and occasionally you can go higher than that. In comparison to I2C, SPI, Serial Peripheral Interface, is a push-pull interface. So it's not open drain, it doesn't require external pull-out resistors, but more on that later, which makes it a tiny bit easier to interface because it's basically just a point-to-point or daisy chain connection. There are various transfer modes for SPI, so there's 4 modes, 0, 1, 2, and 3. We won't go into more detail on this, but effectively it's got to do with clock polarity, phases, and so on. In terms of controllers and peripherals, for example, if we're connecting just a single controller, microcontroller, or FPGA, or any other device to a peripheral, we typically have 3 shared signals and 1 unique signal per peripheral. The first, because this is a synchronous interface, is the clock, which is a controller output. So the controller outputs this clock, and this is typically shared across peripherals if we're using a single SPI bus. Additionally, we have a controller out peripheral in, or COPI, and again, this is a controller output, which is input to the peripherals. The third line is a controller input peripheral output, so CPO or SIPO, and this is again shared across peripherals. We can see this on the right hand side. For example, this daisy chain connection, we have the clock, which feeds from the microcontroller to the sensor, but also to sensor 2, but also to the SD card. So the clock, COPI, and CIPO are shared across the peripherals in this specific example. Finally, however, we have this one, so to speak, unique signal, and this is the NCS or inverted logic chip select line. The N stands for not, so not chip select. Inverted logic, the chip select is active low. This is needed per peripheral, typically, because if we didn't have this line and the microcontroller would start talking, so to speak, or sending data via the SPI interface, all the peripherals would think they're being talked to. So if you want to only talk to one peripheral at a time, we activate their chip select and then we start transmitting or reading data. This is how we can distinguish between peripherals on the same SPI bus in comparison to I2C. I2C we had addressing, and we don't really have addressing here other than these chip select lines. So therefore we have a couple topologies when it comes to SPI. It could either be point-to-point, so we have a single controller and a single peripheral, so only need a single chip select line. We could have a multi-subnode topology, where we have a single controller but multiple peripherals, but only a single chip select line. So we drive the chip select line low and we activate, so to speak, all peripherals. So all peripherals receive the same data from the controller. Lastly, and what's shown on the top right hand side, is the daisy chain configuration, where we have a single controller and multiple peripherals, but also multiple chip select lines. So therefore we can activate each individual peripheral on its own, receive and transmit data to and from these sensors one at a time, so to speak, and they all share a common SPI bus. Of course, it's possible to use several SPI buses, one per peripheral, if your controller supports that many pins, but of course that increases the pin count quite significantly. There are issues, of course, with using daisy chains. That could be loading due to capacitive loading, delays, and so on. Bottom right-hand side, this is taken from a Bosch BMP390 pressure sensor datasheet. We have typical SPI waveforms, and as you can see, we have the chip select bit or NCS line at the top, clock at the bottom, serial data in, and serial data out at the bottom. So there are also different terminologies instead of this controller out, peripheral in, peripheral out, and so forth that you have to pay attention to, but the modern, these days accepted naming is the scheme we're looking at in this video. The way we then perform an SPI transaction is the controller will take a chip select line to whatever peripheral it wants to talk to. Because it's inverted logic, it'll pull the chip select line low. If the chip select line is low, we will then perform either a read or write operation, then the controller will pull the chip select line high again. We can only pull a single chip select line low or make it active at a single time, otherwise we have bus contention. If we have many peripherals that want to put data on the bus with this shared controller in peripheral out line, then of course there's going to be bus contention, we might get short circuits, and that isn't a good idea typically. The nice thing about SPI is, because of the separation with the chip select signals, is that compared to I2C, we don't really have device addressing. Multiple of the same devices can be on the same bus, assuming of course they have separate chip select lines which are required for reading. We talked about loading briefly, but the capacitance on the bus, and this is due to traces, pads, and devices of course themselves, can't exceed the driver specs. So there is a limit to the maximum number of peripherals you can share across a single SPI bus, which will load down the clock, COPI, and CIPO lines. If we have more devices on the same bus, not just because we have to divide up when we transmit and receive data to the various peripherals, but also due to this capacitive loading, which will slow down the edge rates, typically means we get lower maximum speeds as well. If SPI with just a single data out and a single data in line isn't fast enough for you, there are Quad SPI or QSPI and Octa SPI or OSPI options available, which have additional bidirectional data lines. For example, on the right-hand side, we have this QSPI memory. We have 4 bidirectional data lines, IO0 to IO3. We have the clock for synchronization and a chip select signal as well. And this is typically used for memories or even RAM with Octa SPI, and this gives much faster possible data transfer because we now have effectively a parallel bus. We alluded to it earlier that we might or might not need pull-up resistors on an SPI interface, and this is in contrast to an I2C interface where we definitely do need pull-up resistors on the SDA and SCL lines, as that is an open drain interface. For SPI, we have a push-pull interface, so we have dedicated output drivers that can pull the line high or low without the need of external pull-up resistors. However, I do recommend putting at least pull-up resistors on the chip select lines. So per peripheral, per chip select line, we want 1 pull-up resistor, so 1 per peripheral. For example, on the device we see on the right-hand side, this is an inertial measurement unit, contains an accelerometer and a gyroscope, and actually, effectively there are 2 SPI peripherals internally to this one IC. That's why we also have 2 chip select signals, so NCS-ACC for the accelerometer and NCS-GYR for the gyroscope. Each of these, I've attached a pull-up resistor, fairly high value, to the system VDD-IO voltage. In this case, it's 3.3 volts. The reason for this is, at startup or whenever the chip select signal isn't actively being driven, for example by the controller, it's floating, its state is undefined, we could have the case where multiple chip selects are floating to an active state, and therefore we have bus contention because multiple peripherals on the same SPI bus are driving, for example, the CIPO line. This can also happen, of course, with a single peripheral and a controller which isn't initialized yet, and we might get some sort of bus contention, 2 outputs trying to drive each other and so on, and we can prevent that by pulling the chip select lines high with a high value resistor to prevent these lines from floating at startup or when they're not being actively driven. Remember, the chip select line is inverted logic, so if chip select is pulled high, the peripheral is disabled and we can't get any bus contention, which of course could lead to short circuits and so on. So I'd strongly suggest adding those in. Sometimes it's also recommended to do the same thing on the CIPO line, so the controller input, peripheral output line, again for similar reasons, but typically I don't actually add this on, but I definitely add on the chip select line. Now, the next point regarding pull-up resistors, this is not strictly an SPI problem, but some flash memories, they can work either in, for example, SPI or QSPI mode, and if in SPI mode, we have 2 additional pins, which, if not in QSPI mode, may double as write, protect, and hold pins. So if I just go back one page, for example, the flash memory you saw at the bottom right, this is a QSPI flash memory, but it can also work in SPI mode, so which is a single data line in, single data line out, so that's IO0 and IO1. If you're using it in SPI mode, IO2 and IO3 are actually inverted logic write protect and inverted logic hold or reset pins. And if they're floating, the state is pretty much undefined on these pins, and you might get problems there, for example, that a write protect is enabled when you don't want it to, and so on. So make sure, if you're using, for example, QSPI memories or any other peripherals that might have similar issues, in SPI mode, make sure to add pull-ups to those lines. In terms of recommended value, there isn't really a strict value you want to go with. Of course, if you have a lower value, that might increase current consumption if you're driving the line in the opposite direction. Therefore, typically tens of kiloohms and even up to about 100 kiloohms for a pull-up resistor is typically okay. What I like to do is, of course, bill of materials consolidation, so reducing the number of unique entries on my bill of materials, which makes assembly, inventory, and so on much easier and cheaper. So use whatever you have in the design of a similar order of magnitude. Point that's often asked is if SPI requires termination, if it requires impedance control, and if it requires delay matching. We'll go through this in a bit more detail, but to be honest, in many situations, pretty much none of this is required. However, that is an if, so there can be, of course, situations where you do want to do this. In essence, and in general, every time we talk about termination and impedance control, we require this typically, or we should plan for it, if we have fast edge rates, so very short rise and fall times, and to get those, we can look at IBIS files and sometimes datasheets, and in comparison to those fast edge rates, we have long traces. So this is again looking at critical lengths and so on. If we have fast edge rates and comparatively long traces, this can result in reflections, ringing, reduced signal integrity performance, an increased EMI signature which can lead to problems, and more. I won't be going into detail here, but make sure to check out video number 64 on my channel, which goes into more detail of how you can see when a trace is long and short compared to rising and falling edges and those rates. If you happen to be using or needing impedance control in other aspects of your design, for example, if you're routing RF or routing any other high-speed digital, for example, DDR memory and so on, if you have impedance control anyway in your design, you may as well route SPI as 50 ohm traces as well, but it definitely isn't required in most cases. Same thing also with delay matching between traces is not typically required. Oftentimes it's recommended that you route the clock signal longer than other signals, but generally none of this is required. But keep in mind always to calculate your timing margins if possible, but oftentimes in SPI cases you can definitely get away with it. Remember that clock frequencies are about 10 MHz for timing margins, and that we can expect for such a clock frequency as a rough rule of thumb to have about a tenth of the period for the rising and falling edges. So that would be about 10 nanoseconds falling and rising edge times, so comparatively slow to most modern interfaces. If we do need termination, what we want to use is series termination, not parallel termination. Typical SPI drivers simply aren't strong enough for very low value resistors or very low parallel termination, therefore we have series termination. Series termination, for the top right picture, we have an output driver and we want to place a series termination resistor very, very close to the output driver, so very close to the output pin of our SPI line. I do have a video on series and parallel termination basics, so make sure to check those out if you're interested. I typically will add in series termination at least as placeholder values, and this I think is good practice unless the design is very, very small and you're very sure that you don't need it. So I'll put placeholder resistors, so to speak, at the output drivers. So at the controller, that would be the clock pin, at the controller out peripheral in pin, and at the peripheral, that would be the controller in peripheral out pin, because that is the driving pin of the peripheral. And you can see that on the right hand side. So at the controller side, we have a clock, copy, termination resistors, and at the sensors at their outputs, so the CPO pins, CIPO pins, we have these termination resistors on that side, so close to the output driver. Typically, the chip select lines do not need a termination resistor, but you can put one in for good measure. What I typically do, I typically actually only put a termination resistor at the clock output, and this will either be a placeholder value, it might just be a 0 ohm resistor that I can then tune later, but at least I have it on the design. Unless the output driver impedance known, and in many times it's difficult to know the output driver impedance, a good starting point for a termination resistor value might be something like 22 ohms. Again, this is something you need to tune and measure on the real PCB, see if there's any ringing, any reflections on the signal lines, and if they are causing issues, that could be data issues or could be EMI issues, you can increase the value of those placeholder termination resistors. So if you have them in the design, it's much easier to tune them than to respin a board and add them in later. Again, in many situations, none of this is actually required. Just looking at an example where I did place termination, and this is just on a clock line. So I have this AMD Xilinx Zinc system on chip, which connects via QSPI to some non-volatile flash memory on the left-hand side. At a 2D view, we have the clock signal coming out of one of these pins on the BGA package, and as quickly as I can, close to the output driver, I'm placing this 22 ohm series resistor, which then feeds on into my QSPI memory. Just as a very, very simple example, I've really only placed a very small bit, so to speak, of termination at the output of my driver, so the clock pin of the controller, which goes onto my peripheral, this QSPI flash memory. But to be honest, given the length of these traces and the distance between them, it's not really needed, but I typically always put it in for good measure in case. Now we've discussed the basics, let's have a look at some real-world schematic tips and PCB design tips, and then look at some real-world hardware, how it's actually been implemented. Again, SPI, same as I2C, is a very, very simple interface. There's not much really that can go wrong, but of course there are some things to pay attention to. One thing is, of course, the voltage level. So sometimes you might have an integrated circuit that has separate voltage inputs or power inputs. One might be the core voltage, one might be the I/O voltage, and of course we want to make sure that the I/O voltage between peripherals and controllers matches. Check the recommended operating conditions, the I/O high and low levels of the datasheets, but try to keep your VDD I/O levels, of course, the same. There are sometimes margins you can live with, and sometimes you'll have to use voltage level translators. Sometimes also ICs will have a mode select pin, so you can select between SPI interface or an I2C interface. For example, this IMU on the right hand side, this Bosch BMI 088, you can see pin 7, the bottom left of this IC, is the PS select pin. Now I've written on the schematic that if PS is pulled low, this actually becomes an SPI interface, and if PS is pulled high, this becomes an I2C interface. So make sure you've got the right mode selected. If you have multiple peripherals, you will typically want one chip select pin per peripheral, unless you're performing writes at the same time to many peripherals, but you can't really do reads in that sense. So one chip select per peripheral if you're sharing the same SPI bus. And this is a very important point because you can improve the throughput, for example, if you're running DMA streams, if the peripherals are on separate SPI buses. Remember, even though if you have multiple peripherals on the same SPI bus, the access is limited to one at a time. Whereas if you have several SPI buses, you can have accesses in parallel, for example, if you use DMA or multiple cores and so on. That does, however, increase the complexity and signal pin count. We also have to be worried about required speeds and bandwidths. For example, if I'm sampling data from an inertial measurement unit, I want to get that quite quickly. I might want to have less devices on the same SPI bus, and this could be for loading reasons, it could be for timing reasons, and you might want to split up your SPI buses as before, or maybe even go with QSPI or OSPI options. If you're routing SPI on the PCB and then going off-board via connector, you might want to add in some filtering in those lines. So for example, some pi filters. You might want to add series resistors for short circuit protection and also for termination before going off board. You will also want to add ground returns next to the SPI pins for improved signal integrity and EMI performance. Again, talking about termination, unless the board is very small and cramped, I would suggest at least one placeholder resistor, so that could be 0 ohms or 22 ohms, a series termination resistor at the clock driver output. So from the controller, place a small series termination resistor that then feeds the clock lines. As a bare minimum, I would suggest. In terms of PCB design, again, SPI is a very, very simple interface. There is not terribly much that can go wrong. We want to follow the usual PCB design best practices, so that is a root above a reference plane, ground ideally, or a plane that has the same voltage as the SPI interface, don't cross splits. Follow the usual good practices. Keep distance between the SPI traces and other SPI traces, and between SPI traces and any other traces, power, lines, components, board edges, and so on. And this is the 3H rule, as usual. So if you have a dielectric thickness of H, you want to space out your traces and so on, at least 3 times the dielectric thickness. Keep traces as short as possible. This minimizes the capacitance due to the trace. It can lower the crosstalk, emissions and noise and so on. So if I can, don't make your traces unnecessarily long or route them excessively. Don't also make your traces excessively wide. These SPI lines are not carrying any power, well, close to none, and increasing the trace width unless necessary just adds unnecessary capacitance. You don't want to also make them too narrow either, so you get into manufacturing issues and it makes your board cost more, but we'll see more about that in the later practical examples. If you're routing from one controller to multiple peripherals, don't route with stubs, so this sort of star configuration, but rather through the devices, and I'll show you what that means in just a second. The pull-up chip select example locations are not critical, but typically they are placed close to the peripherals themselves. Again, controlled impedance, if we're using controlled impedance in the design anyway, you may as well route SPI as controlled impedance as well, if you happen to have that in the design already, and typically that would be at 50 ohms. Termination again, if you're using it, place it close to the output drivers. So identify the output drivers, place your series termination resistor with a lumped distance from that output driver pin. Now let's look at some practical examples. I'll show you how to route this out and what a schematic might look like. The first board I'd like to show you is that at the start of the video, this micro quadcopter PCB. Again, we have a microcontroller in the center connected up with various peripherals that most of the time, in 3 cases, use SPI to interface back to the controller and to the controller. In terms of the schematic, looking at the microcontroller section, you can see I'm actually using separate SPI buses and interfaces between the various peripherals. This is again because I want to be able to use DMA and do parallel data transfers, for example, from the barometer, the accelerometer gyroscope, and the RF transceiver, that I don't have to wait for one to complete to be able to talk to the next one, so to speak. So I have my RF, chip select, clock, CPO, and copy, same for the barometer, and same for the inertial measurement unit, and keep in mind the inertial measurement unit had 2 chip select signals, so chip select for the accelerometer as well as chip select for the gyroscope. Now, given the board constraints and the board sizes, fitting on a series termination resistor for the clock and really wasn't really feasible, and to be honest, for the size of this board, generally not really necessary. Therefore, I don't have any termination resistors on this. What I do, however, have is, as we saw before, are separate chip select pull-ups to the 3.3 volt logic at 56k, and that's just reusing values I had before. But other than that, I don't have any pull-up resistors. For routing and layout, I didn't do anything special, so to speak. For example, the controller's in the center, and then I have an SPI connected up and between this peripheral, which is the Bosch BMP390 pressure sensor. I try to place that as close as feasible so I can fit in all of my other components, of course, but not further than I needed to. This meant also rotating the component and selecting the right pin out on my microcontroller, that I simply can have pretty much a straight connection between these two interfaces. So trying to keep my connections as short as possible. You can see here they're only a couple of millimeters, so termination definitely not needed. Connections as short as possible, trace widths aren't excessive, they're about as wide as the pads of these QFN packages, and in this case I just used a fairly small 0.15 millimeters. I would suggest going with 0.2, 0.25 as good starting points, unless you have very strict space requirements, or if that happens to be your controlled impedance trace width anyway. Vias on SPI, we want to try and minimize, but they aren't really problematic. So occasionally you will have to jump, of course, to get to the right pins. And the pull-up resistors, for example, for the chip select line, I'm routing in to the pull-up resistor, out of the pull-up resistor into the chip select line. The pull-up resistor is placed close to the peripheral, and the other side of the pull-up resistor is pulled up with a wide trace to my I/O level voltage. There isn't really much more to that. Now that we've looked at a point-to-point connection, which is rather simple, we can also look at a daisy chain configuration, both from a schematic and PCB design point of view. Now this is a very, very simple demo schematic in PCB, so take this with a grain of salt. This is just for demonstration purposes and doesn't serve a function other than that, and things aren't connected up properly, so to speak, other than, of course, the SPI. So for example, on the left-hand side, we have an STM32 microcontroller, which acts as the SPI host controller, and we want that to interface with two SPI peripherals. I've just randomly chosen two SPI memories here that we want on the same SPI bus, but separated by two chip select signals, so to speak. I've hooked up the first SPI memory, so the clock, CIPO, COPI, and the chip select to the first SPI memory, just as we would with a point-to-point connection. I've added in, for example, as a demonstration, a series termination resistor close to the output driver on the clock line, and the driver is the host controller, so close to this pin 36. I've put this on the schematic also to symbolize later for the PCB designer that this resistor is a termination resistor and should be placed close to this side. Excuse the messy wiring here, but all I'm doing is point-to-point connection, so clock to clock, controller in, peripheral out to the flash memory output, controller out, peripheral in to the flash memory input, and the chip select to the chip select. Now I do have two pull-ups, of course. One is for the chip select signal, as we discussed earlier, and this in the range of tens of kilo ohms. But we also have this other pull-up resistor here, R3, also the same value as this chip select pull-up, because this SPI memory actually can be a QSPI memory. So therefore we have these additional data lines, IO2 and IO3, which in SPI mode double as write protect and hold pins with inverted logic. So these are active low. If we just leave these pins floating, pin 3 and 7, we don't know what state this SPI memory is going to be in. We could have write protect errors and so on. So what I want to do, I'm simply tying these pins together and pulling them permanently via a pull-up resistor to a logic high. So I'm disabling the write protect and I'm disabling the hold. This is of course only true in SPI mode. Now, if you want to hook up a second peripheral, in this case, I've just went for the same thing, so another bit of memory. We need a separate chip select pin, in this case, which I would like to hook up. So I'll take my chip select, hook that up to the other chip select, and this is how I can distinguish between these two devices then. The rest of what we have to do is simply daisy chain these devices up. So the clock simply goes to the clock after the termination resistor. Controller in, peripheral out goes to the peripheral out. Controller out, peripheral in goes to the peripheral in, like so. And this is how easy it is to set up a peripheral daisy chain connection. The data lines are shared and the clock line is shared, but we have separate chip select signals. And again, one pull-up per chip select, and keep in mind if you have these situations with these write protect pins and so on. Now at the PCB design side, again, take this with a grain of salt. This is a simple demo PCB. Top layer is signal and components, and the bottom layer is a solid ground plane. This is just a 2-layer board, very, very basic. We want a solid reference underneath. Same for multi-layer boards as well. What we have is the host controller on the left-hand side, and we have the two peripherals to the right. In this case, these are two SPI flash memories. What we want to do is not place these flash memories as far away as we can, and we don't want to place them too close that we get DFM issues or overlapping components and courtyards and so on. We want to have them a short distance away from the controller and from each other. Unless, of course, you're particularly space constrained or these SPI devices have to be in a specific function, for example, certain sensors and so on, you want to try and place your components as close as you can and as close as is reasonable, which then results in the shortest trace lengths possible, which is what we are aiming for. Per one of these devices, looking at one of these flash memories, we have a decoupling capacitor that of course should be placed close to the relevant power and ground pins. We have our chip select pull-up, which should be placed close to the peripheral, in this case the SPI flash memory, and close to the relevant pin. Same for this flash write protect and hold pull-up. I've placed that somewhere close to the peripheral, and same thing for the other identical copy of this device. Now, of course, the controller and peripheral pinouts might be fixed. You might have some flexibility in moving these around so you don't have as many crossings, but sometimes it just isn't possible and you have to do with the pinout you're given. In terms of placement of the series termination resistor, I don't want to place this, for example, at the peripherals like so. At the peripherals, the clock is an input. I want to place my series termination resistor at the host controller output. In this case, this is pin 36. That's why I place my series termination resistor as close as is reasonable. In this case, of course, I'm not particularly space constrained, as close as is reasonable to this output pin 36. In terms of routing trace widths, unless you're routing with controlled impedance, I typically do something that's easily manufacturable. For example, if I route out of this CIPO pin, it might be as wide as about that LQFP pad, and that's about 0.25, 0.3 millimeters. I want to prioritize, of course, routing my clock and data signals before I route my chip selects, because my clocks and data lines will toggle far more frequently than these chip select lines. So I might start, for example, routing out my clock, out of the clock output driver into the series termination resistor, and out of the termination resistor to wherever it needs to go. Now, there's two ways of routing out SPI if in a daisy chain configuration. For example, this clock, what I could do, I could route out, and keep in mind this is going to be a bit crude, route out into one device, and I could route as a branch topology into the clock pin of the other device. Now, this might be okay if you keep your branches short, but this does mean you get these stubs here. So we're routing one trace and suddenly we're branching off. Might not be the ideal way to do it, but then again, for these speeds, you might be fine. What I prefer to do is I route out my output driver into my first device. Now, if this is the top or the bottom, it doesn't really particularly matter. Out of that device and then into the clock or the other peripheral. So in this way, we don't have this kind of branch or tree topology. I'm routing through in somewhat of a flyby topology with my series termination resistor to start with. So output driver, output pin, series termination resistor through the devices. And keep in mind, branch topology, especially if your devices are close together, you have short traces, can be fine as well, especially if the branches themselves are short. So you would do the same thing then for the other signals, for example, controller in, peripheral out. You can route into these pins and then through to the other devices as well. You might have to use vias to jump layers and so on. In terms of the chip select lines, the reason we've placed the chip select resistors that close or next to the peripheral is that we can route out from a chip select line through the pull-up resistor, out of the pull-up resistor, into the peripheral itself. And that's where it ends because this is, of course, is not daisy chained, this chip select signal. What I don't want to do is, for example, route into the chip select line like so and do this little stub up like this. There's no real reason for that. Again, out of the output driver, short trace, into the pull-up resistor, and into the relevant pad of the SPI peripheral. I could, of course, change that topology a tiny bit where I route out of the output driver, the chip select pin, into the chip select pin of the peripheral, and then out into the pull-out resistor. So that is an option as well. On the other side of the pull-out resistor, if I have an internal power plane, I'll place a via very close, but not too close to the pad, and a short wide trace from the pull-up side of the pad, short wide trace into the power plane of the via. Or if I'm doing routed power, I would simply have a wide trace coming from my other power traces. So a very, very simple example, but I hope it showed you the difference between routing through versus routing branches and stubs, and how to place pull-ups and how to place components. Thank you very much for watching this video. I hope it was useful and I hope it gave you some basic insights in what to pay attention to when it comes to SPI hardware design and PCB design. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest hardware and PCB design videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.